Okay, so in this video, we're going to go ahead and take a look specifically at the case for rigid body motion of a free rotation. To have a free rotation, that means you have no torque. So, that means that N equals dL dt, again evaluated in the fixed frame. So that tells us, and that will be equal to 0 because it's no torque, so that tells us that the angular momentum of the system has to be a constant. That's all well and good, but still we need to evaluate this in the rotating frame in order to keep our moment of inertia tensor well behaved. So we'll have dL dt in the rotating frame plus omega cross L. So let's just write that as L dot plus omega cross L. That will have to equal 0. So that gives us that L dot will equal minus omega cross L. So what we get out of this is that in the rotating frame, the angular momentum is not a constant. We can see that it is changing. However, we know that its magnitude is a constant because our dl from our L dot here, that's perpendicular to L because we've got this cross product here. So that tells us that only the direction changes. So at the very least, we know that the magnitude stays put. So in our rotating frame, we can at least say that L squared, which is equal to L dot L, is a constant, even though the vector L itself is not a constant. Okay. So, as per usual, we can go ahead and work in the coordinate system aligned with our principal axes. So then we can write our L squared as an E1 hat I1 omega 1 plus E2 hat I2 omega 2 plus E3 hat, I3 omega 3 squared, which when you write squared on a vector like that, this just means dot it with itself. So dotting it with itself, we'll get I1 squared omega 1 squared plus I2 squared omega 2 squared plus I3 squared omega 3 squared equals a constant. Well, if we think about that for just a moment, we realize that this is an ellipsoid. And this would describe an ellipsoid in omega space, where our principal diameters are in the ratio of 1 over I1 to 1 over I2 to 1 over I3. All right, but that's not all. We can also argue that the rotational kinetic energy has to be a constant. After all, there's no torque, right? So since the rotational kinetic energy is a constant, we can write that as 1/2 omega dot I dot omega. Yeah, I know I should really make that little half arrow point to the left, but I think we know what I mean. Equals a constant. So writing that in matrix form, that would be in omega 1, omega 2, omega 3. Oh, what the heck, I will make that little arrowhead point to the left. There we go. Times I1 0 0 0 I2 0 0 0 I3 omega 1 omega 2 omega 3. That has to equal a constant. Well, we go ahead and follow that through. We get that 1/2 times I omega 1 squared plus I2 omega 2 squared plus I3, whoops, I3 omega 3 squared. That has to be a constant. Well, I can multiply by 2 to get that and get this by itself, and it'll be a different constant. It'll be 2 times the rotational kinetic energy for what it's worth. But this is also an ellipsoid. And in fact, it's called the Poinsot ellipsoid. And here the diameters have to be in the ratio of 1 over root I1 to 1 over root I2 to 1 over root I3. So we've got this restriction that at all times as the body rotates, the angular velocity vector has to precess in such a way that it follows the intersection of the two ellipsoids. So, Lord help us, I'm going to try and draw it. So this would be, say, one of the ellipsoids here. Trying to draw this in some kind of 3D. That's probably not going to work out so good. This will be one of the other ellipsoids coming down from here, intersects, goes in like that, back down to there, around like that. And then the key bit is right here is going to be our intersection of the two ellipsoids. I should draw that in a different color. Let's make it orange. Something like that. And so at all times, omega, let's point it somewhere else where we can see it a little better maybe. So at all times, omega has to follow along this intersection that we found between the two ellipsoids. All right. So we can look at some special cases. For the sake of argument, let's just say that I3 is greater than I2 is greater than I1, just so we're in some sort of agreement. Okay, so one special case would be if the angular momentum is equal to I3 omega E3, right? There'd be no precession in that case because the ellipsoids would only touch at that one specific spot. So from your text right here, the angular momentum ellipsoid and the Poinsot ellipsoid, in this case, will intersect just right there. And so omega is forced to just keep pointing at that point forever. Okay. And similarly for the case of L equals I1 omega E1, going back to the illustration in your text, that we just switch which ellipsoid is which, but now the but again, you're constrained to just go to that one point because it's the only place where they touch. So in both of these cases, there will be no precession. But now let's say we pointed along the intermediate principal axis. So we've gone with the biggest and the least. Let's go with the intermediate axis. L equals I2 omega E2. There will be precession there. As you can see right here, where the two ellipsoids intersect, omega will precess along a path that always touches that intersection. You can actually demonstrate this for yourself, and I would encourage you to give the video a pause and try it. The easiest way to do it is just to take a book, as long as it's not like some funky square shape, but just a normal book. You'll want to keep the book from opening when you toss it in the air. So if you've got a couple long rubber bands or some binder clips, something, string, whatever, come up with something to keep the book from opening up when you toss it into the air. And then what you can do is you can toss it along the long axis. That would correspond to the x1 axis because the moment of inertia will be the least there. You can toss it around the short axis. That would correspond to the 3 axis because that's where the moment of inertia will be the greatest. And you'll find that both of those will tumble very stably. But if you toss it around the axis in between, you'll see that the book will tumble. And there's absolutely nothing you can do to make it go any smoother than that. So tell you what, why don't you go ahead and pause the video and give it a try and come back with me. Okay, glad to see that you've come back. So let's go ahead and look then at the case of the force-free motion of a symmetric top. So we'll have I1 equals I2 is unequal to I3. So I'm imagining, like, say, a gyroscope, something like that. So this will be my x3 axis, like so. This will be my x1 axis, and then x2 will be perpendicular to the 2, pointing into the page in this case. All right. So you can go ahead and write Euler's equations of motion here for all 3 components. So n1 will equal I1 omega 1 dot minus, so remember 1, so then we'll have 2, 3, I2 minus I3 omega 2 omega 3. And 2 equals I2 omega 2 dot minus, so then that's going to be 2, 3, 1, so I3 minus I1 omega 1 omega 3. Then finally we have n3 equals I3 omega 3 dot minus the 3 becomes 1, 2, I1 minus I2 omega 1, whoops, omega 2. All right, but we said that I1 and I2 are equal, so let's just, everywhere we see an I2, let's replace it with an I1. Oh hey, that makes this term here go to 0. So we get that immediately. Also, let's not forget that since this is torque-free motion, all the components of n are also 0. So our Euler's equations of motion become I1 minus I3 times omega 2 omega 3 minus I1 omega 1 dot equals 0. Then let's see, from here we're going to get I3 minus I1 omega 1 omega 3 minus I1 omega 2 dot equals 0. Then lastly we're left with minus I3 omega 3 dot equals 0. All right, so from this last equation we can immediately conclude that omega 3 is a constant. All right, so that leaves us for our equations of motion with omega 1 dot being equal to I1 minus I3 over I1 omega 3 times omega 2. And then by the same token, we'll have omega 2 dot is equal to I3 minus I1 over I1 omega 3 omega 1. All right, well, let's let this I3 minus I1 business right here, let's let that be defined to be omega, capital Greek omega. Sorry, this I1 minus I3, yeah. So we'll go ahead and, no, sorry, this guy right here. We'll go ahead, we'll define this guy here to be capital Greek omega. So by the same token, this becomes minus capital Greek omega. And then we can rewrite this into something closer to a standard form of omega 1 dot plus omega 2 equals 0. And omega 2 dot minus omega 1 equals 0. Okay. So we go ahead and look at this. We remember that we solved some stuff like this a long time ago, doing something similar. So we can go ahead and invoke the method of complex exponentials again. So the trick here is we're going to times this second equation by I, and then we're going to add them. So you get omega 1 dot plus I omega 2 dot plus omega minus I omega 1 plus omega 2 equals 0, and omega 1. So, all right. I can rearrange it just a little bit. Omega 1 dot plus I omega 2 dot, just trying to get into something closer to a standard form again, equal minus I. I can pull a minus I out of both of these. I'll have an omega. This leaves me with omega 1 plus I omega 2 equals 0. Excellent. So following our prescription from before, we can define this combination to be eta, which means that's eta dot. All right, so we have eta dot minus I omega eta equals 0, and we know how to solve that. That's going to be eta is equal to some omega naught e to the I capital omega t plus some arbitrary phase constant delta. Now, by clever choice of when we decide that when t equals 0 happens, we'll just set delta to 0 just to make things a little easier. So, okay, that lets me break the solutions back apart. Omega 1 plus I omega 2 will be equal to omega naught. By the Euler identity, this will be cosine omega t plus I omega naught sine omega t. And we can go ahead and equate the real and imaginary parts. So we get that omega 1 is equal to omega naught cosine omega t, and omega 2 is equal to omega naught sine omega t. Super. And remember, omega 3 was a constant. So just as a quick sanity check, we would certainly hope that omega remains a constant. So let's just verify that. So omega, magnitude of omega would be omega 1 squared plus omega 2 squared plus omega 3 squared. So that will be root. We'll have an omega naught squared cosine squared omega t plus omega naught squared sine squared omega t, plus omega 3 squared. Well, hey, sine squared plus cosine squared, right? So this is omega naught squared plus omega 3 squared, which sure enough is a constant. So at least our sanity check is preserved. So to understand our solution here, let's go ahead and draw this in the what we call the body frame. So this will be x1, x2, x3, like so. This would be my vector omega. It will process around with frequency capital omega, like so. This projection right here is our omega 3. If I project down into the x1, x2 plane, this would be our vector omega naught. And then this would be our omega 1 and our omega 2, like so. And this would also be processing around. All right. Now, we remember that the rotational kinetic energy is 1/2 omega dot I dot omega. So this will be 1/2 omega dot L, which is a constant. So what this means is that not only must our omega process to maintain a constant projection against x3 in the rotating frame, but it's also got to project in such a way that it has to process in such a way that it maintains a constant projection along the fixed angular momentum in the space frame. So I'm going to draw the space frame here in black. So there's my angular momentum vector, like so. All right. So it's got to project around. No, we can keep that in blue. Why not? Okay, so omega has to process around in such a way that maintains a constant projection onto L. Now, it doesn't have to be this length. I'm just drawing it for simplicity's sake. It could be longer, could be shorter. It just has to maintain a constant projection. It also, so we'll call this my x, y, and z. So we can say that the angular velocity vector has to move around the surface of what we call the space cone, like so. At the same time, in the rotating frame, so say this is my omega 3, like so, or sorry, my x3 axis, like so. And then we'll just draw x2 and x1 mutually perpendicular. Oops, that has to go into the page the way I drew it. Something like that, maybe? I don't know. Anyway, omega has to maintain a constant projection against x3. So that also means that it has to at all times traverse along on this, what we call the body cone. So as it processes, what you can imagine is that the body cone is rolling around the space cone and the with frequency omega, capital omega, and where they intersect is where the angular velocity vector points at any given time. We can show that this x3, by the way, has to always lie in the plane of L and omega. That's probably instructive to demonstrate, so let's just do that real quick. Let's dot L into omega crossed with E3. All right, so that's going to be L dotted with omega 2 E1 minus omega 1, E2. All right. And then projecting in what L is, L, remember, those can be E1, I1, omega 1 plus E2, I2, omega 2 plus E3, I3, omega 3. And we have to dot that into omega 2 E1 minus omega 1 E2. All right, so the E3 dots into 0, it goes away. So we look at these terms here, and again, I1, omega 1, omega 2. Here from this term I'll get, and we get a minus on that, right? Yeah. No, we get a plus, sorry. And then from here we'll get a minus I2, omega 1, omega 2. But remember again, omega 2, I2 is equal to I1, so that's equal to 0. So that means that the x3 plane is indeed lies in the plane of L and omega. Otherwise, we would have a non-zero dot product. All right, so we can conclude then that that capital omega is indeed the precession rate. All right, that's a bit, I found a good animation to check out showing that precession. Oops. Well, I thought I did anyway. Oops, my bad. Oh, do not do that to me. Here it is. So what we've got here, this is my top, like so. The blue here is my E3 axis. This is my angular momentum. And I go ahead and let it precess. This black cone here is the space cone. This blue cone here is the body cone. And we can see, sure enough, the two cones do roll around each other, and omega is always sitting at the intersection of the two. All right, something I forgot to do a little earlier, but I'll just go ahead and toss it in now, is the book did take a look at the case of doing a numerical solution for free rotation of a rigid body with 3 different principal moments. And so this is a phase plot of my omega 1, omega 2, omega 3 components here. I just put in the ellipsoid in a ratio of 1 to 2 to 3. And you can see that that in general it does bob around like we had expected before. This right here is the intersection of the Poinsot and the inertia and the angular momentum ellipsoids. All right. So the next series of lectures will be a continuation on to the motion of rigid bodies in 3D, looking at some more advanced cases.